This is a man-made motor, a motor so small that more than 6,000 of them would fit on the head of a pin. Welcome to the world of the nanometer, a unit of measure that is 1/billionth of a meter.
A nanometer is pretty small. One of the best analogies that I like to use is to compare it with a human hair. If you take a hair off of the top of your head, you can see that it's very thin. And now if you take something that's 100,000 times thinner than that, that's a nanometer.
The ability to observe and construct things this small is at the heart of nanotechnology. And what scientists have discovered is that at the nanometer scale, everyday materials start to act in unimaginable ways. For Jeffrey Grossman, a UC Berkeley nanoscientist working with the National Science Foundation, that's exactly the draw.
The behavior of nanomaterials changes, or can change, when the size becomes so small when compared with a larger amount of that same material. When you have things that sort of start changing the way they behave, and now you have the ability to control that, it sort of opens up an entirely new phase space of material.
Suddenly it's like the periodic table projects out into a new dimension. It's not just that we have the list of elements, it's where we can change their sizes, and each size is a little bit different than every other when it's very, very small.
The fact that you can customize nanomaterials' unique behaviors has already turned nano into the buzzword of the decade. Some researchers predict nanotechnology could lead to faster computer chips, tiny medical devices that repair clogged arteries, and new filters to clean water pollution. As novel as nanomaterials seem, humans have actually used them for hundreds of years. For centuries, the colors in stained glass windows, for example, have been the result of a controlled heating and cooling process that adjusts the size of tiny crystals in the glass.
That's medieval nanotechnology. What's different now is that we have the ability to look on the nanoscale and see what's happening. That gives us an ability to design materials rather than to just find them by a kind of accidental process.
But understanding and controlling how nanomaterials act can be tricky.
Every time you chop the material in two, say you go from a crystal that's 100 atoms across to 50 to 25, each time you do that, almost all the properties of the material really change.
So these changes are very radical and quite dramatic. If you take a piece of a material, say silicon, and you look at that material, it looks kind of dark charcoal, so it's not that interesting to look at. But now if you take out your little nano ice cream scooper and you scoop out a nano-sized chunk of that material, and you look at that, all of a sudden it glows blue. And if you take a slightly bigger ice cream scooper out, it glows red. And so now you have a material that completely changes the way it looks, the color that it is, just by changing its size.
So the question is, why do nanomaterials behave so strangely? In the case of the nano ice cream scoop, the behavioral change happens when you start to make a material so tiny that its electrons are squeezed into a space smaller than they prefer. It's called quantum confinement.
The smaller you make the crystal, the higher the energy of the electron will be. Its kinetic energy is increased, and that can be thought of as making its wavelength a bit shorter and forcing it into a box where it kind of zips around more quickly.
Another factor that shapes nanoscale behaviors is the relationship between volume and surface area. Things this small have much more outside than they have inside.
The surface area of the material starts to skyrocket compared to its volume. And in fact, when you get down this small, most of the material could be just surface, and very little of it is actually volume. And the reason why that's interesting is that the more surface you have, the more reactions you can carry out on that surface, so you can do things like filtering much more efficiently. So you could filter water more effectively with more surface area.
Our ability to observe and change things at the nanoscale has led to a host of new materials applications, and has even made it possible for scientists to begin building working nanomechanical machines like this motor. But in the world of nanomachines, nature is still king.
Some of the most fascinating things that we see on the nanoscale are the machines that nature builds on the nanoscale. Nature makes rotors and motors and things that operate on this length scale of a few nanometers by making protein assemblies and that have these interesting nanomechanical properties. If you look at the flagellum of a bacterium, it's a little nanoscale motor, and it has bushings and all kinds of little pieces inside there that is built very differently than the way we make ours. And they have some other tricks they're trying to decipher.
Ali Visatos and his colleagues are eager to understand and apply some of these new ideas to the real world. Among their goals, finding new forms of clean energy. Every minute, enough of the sun's light reaches the Earth to meet the world's energy demand for an entire year. This seems like a good place to start.
Photosynthesis and photovoltaics is surely the one where we have the most interesting conversation that goes on between how nature achieves this and how might we do it in the future. If we're to get our energy from the sun, we need to copy some of the lessons of nature, but we also need to find some of our own little tricks that we could apply.
Coming up with some tricks of their own. That's exactly what researchers are doing at Lawrence Berkeley National Laboratory's Molecular Foundry. Located in the Berkeley Hills, the facility is one of the world's premier nanoscience research centers. Comprising 6 floors, the foundry is a buzzing hive of activity where the newest nanomaterials move from theory into the lab.
We're working on developing plastic solar cells, so trying to harvest light for energy using polymers and more like nylon.
Traditional solar cells using crystalline silicon as the light-absorbing material are less than ideal. Silicon is heavy, expensive, and fragile. In this lab, researchers are trying to replace silicon with polymers, complex, usually man-made molecules. Here, graduate student David Kavalak builds tiny polymer-based solar cells and tests the results.
We're focusing in a solar cell on the active layer of the part that does the light absorbing and the conduction of the electrons to the electrodes. We can design these conjugated polymers that are conducting in any number of ways. We can add on certain side chains to them that make them more soluble, that make them better conductors, that change the energy levels and the band gaps of these polymers. We start with a glass substrate with a transparent electrode, which is normally indium tin oxide. We spin a polymer solution down on top of this, which the solvent evaporates really quickly, and we're left with approximately 100 nanometers of polymer, which is our active layer. Then we take it, evaporate on a top contact electrode, and test it in a solar simulator. We have 8 aluminum electrodes that gives us 8 solar cells per substrate. And so now we can use this to test and see what kind of efficiencies we've gained. We have the ability to control individual molecules in the polymerization steps, and we're just on the very cutting edge of this. It's only been around for so few years that we don't know where this is going to go, but it only looks up.
But along with its promise of a bright new future, nanoscience brings with it a share of risks and fears. In December 2006, the city of Berkeley amended its hazardous materials law to include nanoparticles, making it the only local government in America to regulate nanotechnology.
We know that nanoscale materials can enter inside cells, and we know that that could have consequences for health. And so it's incumbent, it's really required that we do research to understand what is the nature of the interaction between new engineered artificial nanoscale materials and living systems, not just cells, but whole living beings.
I think when you understand what kind of impact nanotechnology could have on some of the global problems, such as global warming, disease, clean water, and so forth, I think that inaction is actually the unethical standpoint. I think stasis is unethical in this case.
These advances that we're describing today are really key to achieving health and to achieving sustainable energy technology, the big issues of our day in many ways. And so I think every member of the public has an obligation to try to learn a little bit about these things so that they can participate in that debate in a meaningful way.